So I decided that maybe it shouldn't be due next week, since it would be really, really hard. Because we're talking about the content here that you need for those labs. So maybe we should wait until the 15th. So that is the major change, is that the results lab, has moved from next week to here. That also helped because I only got 1/3 of the labs graded, and so Monday then we'll have all of them. It does mean your results lab, you don't need to turn in your notebook, so that should be okay for notebook lab. But you may need to copy some data when you turn in that, when you do your FTR. We'll talk about that more when we get there. It does mean lots of stuff to do at the end. So when you can do calculations, things like yield and interpreting your spectrum, and more questions, do those, because that will save you time later. The other change is that those groups who did the second week of F this week are now doing E next week instead of G. And that's because of some NMR problems and wanting to have a little more attention on the NMR. And not starting a new lab helps that. So E is already set up, and lots of people have been doing it. There's lots of resources for those who need it. So this is the new schedule. I'll post it on Blackboard as well. It also has names to go along with the group numbers, so hopefully you won't lose your place. Okay, and then, since I was looking at our course schedule, I thought I'd point it out to you as well. If you are taking this course Writing Intensive, you need to be thinking about your big report, or your big thing. I accepted all of the topics, or the revised ones that were turned in. And so an outline and references for your papers are due on Wednesday. Okay, so collecting data, putting it together. That way you'll have a start. I'll know whether you're finding the right kind of materials to actually be able to write your paper, or if we need to work on figuring out more resources. All of these presentation developments, which you are doing right now, you're wondering, how the heck are we going to have an exam over those? Okay? And so I have a first set of questions that I will post that will be a homework assignment that takes some of those, and I will post questions that are exam-like, whether they come from your exam questions or things that I have based on the presentation. And so you'll have lots of questions to pull from, and then some synthesis questions that are homework that I'm writing. So I'll post homework today, or they probably post in the morning. That'll be for the material that we've covered this week in presentation. Well, now you don't have a lab report, so now it'll be next Wednesday, homework. Before break. Just the ones on the presentations this week. So you don't end up being stacked up too much after fall break. Or getting lost.
Is there any chance that for fall break we use exam study material and posted?
Likely? For sure? Take care. Questions? Our schedule, what we're doing. So, we are going to take presentation time. So, you guys want to start? If you didn't get a comment, an evaluation sheet is up in the
16 elements or 5 elements. The first of these is nitrogen. Atomic number 7, 14 grams per mole approximately. It's gas at room temperature, and there's only 20 parts per million of nitrogen in Earth's crust, but it is still the 5th most abundant element because 78% of Earth's atmosphere is nitrogen, which is approximately 4 quadrillion tons of nitrogen, which is a lot of nitrogen. The isolation of nitrogen, this technique was discovered by Daniel Rutherford in 1772. It's isolated by treating a solution of ammonium chloride with sodium nitrate, and small amounts of nitrous oxide and nitric acid are actually produced in this reaction, but these impurities can be removed by simply passing it through aqueous sulfuric acid with potassium bicarbonate. Another isolation technique is this one here, where sodium is produced by the nitrogen and sodium are produced by the thermal decomposition of either barium azide or sodium azide. This one's sodium azide. And some of the practical applications. It's used as protective shielding in the semiconductor industry because it is largely inert. So it's also used in different types of welding and soldering. The liquid form is an inexpensive cryogenic, which we know we use it in the lab. We use it for the superconductor lab, and we used it at the picnic to make ice cream last year at the end of the year. That was really fun. It's also it's used in things like bags of chips are filled with nitrogen so that the chips don't go stale. It's also used in the production of ammonia in a thing called the Haber process. N2 gas and H2 gas are added together, and this is the main industrial route to creating ammonia. And next element, phosphorus. Atomic number 15, 30.974 grams per mole. It's a solid at room temperature, but its melting point is fairly low, 44.2 degrees Celsius. When 4 phosphorus molecules come together, it forms what's called white phosphorus, and it is very reactive and it reacts just sitting in the air and it ignites. Actually, so and phosphorus is the 13th most abundant element in the crust at 1,000 parts per million. So the isolation of phosphorus was discovered by Henrik Brand in 1669. Brand was attempting to create the alchemist's stream, which was called the philosopher's stone, which was something that was said to, you could turn any material into gold and had other magical properties. Unfortunately, doesn't exist or has not yet been discovered. But Brand, in trying to discover this philosopher's stone, Brand actually evaporated his own urine, and the leftover remains, basically, he was left with a white material, which he reported as, it glowed in the dark and it burned brilliantly, and so it was named phosphorus mirabilis, which translates to miraculous bearer of light. His process, it originally involved letting his urine stand for a long time until it started basically rotting, and then he would boil it down, and it would form a paste, and they would heat that paste and lead the vapors through water. He hoped that would then condense into gold, but no, it only condensed into phosphorus. So, not as amazing a discovery as he wanted, but still an important discovery because phosphorus is an important element we use. And it was later discovered that it was unnecessary to have the urine rot. As rotting urine yielded the same amount of phosphorus. Some of the applications is a major constituent of fertilizers. because phosphorus is usually found in phosphate, which is required for all life, and is often one of the limiting nutrients for crops. So it's found in a lot of fertilizers, especially in agriculture and farm production. And it's found usually in the form of concentrated phosphoric acids. Also in matches, phosphorus-containing matches were first started produced in the 1830s, but instead of using the red phosphorus that we use today, they used white phosphorus, which as I said, is very reactive. And some of the problems with this were that basically the match, it could go off by touching any sort of surface. Like with red phosphorus today, we can kind of throw matches around and they won't ignite, but white phosphorus would. And so they were very unsafe, and they were actually fairly toxic. So up until about 1872, they were used until people started realizing that things were catching on fire because of the white phosphorus. And that's probably not a good thing unless we're trying to set them on fire. So now we use safety matches with red phosphorus instead. In water softening, sodium tripolyphosphate made from phosphoric acid is used in some laundry detergents, and it softens the water and it essentially allows the detergent to clean better in the materials, and it also prevents pipe and boiler tube corrosion.
So next up is arsenic, topic number 33, and as you'd imagine, it's a lot heavier than the previous ones anyway on the column. It's solid at room temperature, and its melting point is incredibly high compared to phosphorus, for instance, at 816.8 degrees Celsius. And it's only 1.5 parts per million of Earth's crust, but soil can contain anywhere from 1 to 10 parts per million, depending on where you are. So Albert Magnus, who's known as Albert the Great, he was around 1993 to 1280, and he's believed to be the first person to actually isolate arsenic within the compound in 1250 by being soaked together with arsenic trisulfide. But then later on, German chemist Johann Schroeder in 1649, he published 2 different ways of preparing arsenic. And crystals of the elemental arsenic were found in nature, but they're incredibly rare. So here's some kind of interesting uses. These aren't practical applications, of course, but we found while we were researching arsenic. And so in the Victorian era, white arsenic, or arsenic trioxide, was mixed with vinegar and chalk, and then women ingested it in order to give their skin a more pale complexion so they didn't look like they worked in the fields. And then they also just use it just plain arsenic rubbing on their skin to kind of get the same effect. And so more recently, it's used as a food additive in poultry and swine. Although there's a Poison-Free Poultry Act of 2009 that's attempting to stop that use. And so the actual company that produces it voluntarily stopped selling it. But then, so that company's named Alpharma, and the new company has come up, the successor Zoetis, which continues to sell a compound called Nitarsone, which is that. And it's currently still being used for turkeys and in small amounts for chickens and swine. And also in the 18th century, they used arsenic as a stimulant. Practical applications. So in the military after World War I, the U.S. built a stockpile of about 20,000 tons of lewisite, which is a compound that contains arsenic in it. It was used as a vesicant, like a blister agent in war, and it was also used as a lung irritant. And so that was neutralized with bleach and then dumped into the Gulf of Mexico in about, during the 1950s. And then Agent Blue was used during the Vietnam War, and it's a mixture of sodium chloride and its acid form. And it's basically to deprive the invading North Vietnamese of the foliage that they used to hide it. And it's also used in alloys, so it's being combined with lead, and it's used in like car batteries. But it's only using about a few percentage total of arsenic, so it's not necessarily a dangerous level. And then also we've learned from, I think previous people talked about with gallium, it's used combined with gallium for superconductors. And it's much more expensive, but it's also a lot faster than traditional superconductors. All right, antimony. So this is topic number 51. It's also, once again, much heavier as you go down the list. And it's a solid at room temperature. Has a melting point, also pretty high, although not as high as arsenic of 630.6 degrees Celsius, and only about 0.2 to 0.5 parts per million near its crust. And the abundance of it in Earth's crust is pretty much comparable to thallium or silver in Earth's crust. So the first European description, which we have, was discovered by Vanocchi, Berengruccio in 1540, which predates, there's a traditional knowledge that it was actually discovered in 1556 in a book, but this will predate that. And so the book, which was, I think it's an Italian name, but I'm just going to go with English translation, the Triumphal Chariot of Antimony, which describes the preparation of the metal form of it. And you can kind of see the different synthesis methods to separate it out. And so the sulfide is converted to an oxide, and advantage is often taken of the motility of antimony 3 oxide, which is recovering from roasting, and this material is often used directly for the main applications. Impurities are being arsenic and sulfide, and isolating antimony from its oxide is performed by carbothermal reduction. So these are practical applications. Now, something that was interesting is about 60% of all antimony use is in flame retardants, and about 20% is also then used in alloys. And so it forms a highly useful alloy with lead combined, and it increases its hardness and mechanical strength of the alloy. So in lead acid batteries, this addition improves the charging characteristics and reduces the generation of unwanted hydrogen during charging. And it's also used in pigments, and so it's used as a pigment, and then also as in when they're producing flat screen televisions and other TVs, it's used to prevent bubbles popping up in the screen. And then it's also used as a stabilizer and catalyst for the production of polyethylene phthalate.
The last element is bismuth, atomic number 83. It is actually the heaviest non-radioactive element. It's a solid room temperature. It's about 0.025 parts per million abundance in the Earth's crust, which is about twice as abundant as gold. And the most common ores are bismuthinite, or bismuth sulfide, and bismite, which is bismuth oxide. Bismuth it's been known of since ancient times. For example, the Egyptians and Incas were known to use these in different applications, but Claude Francois Geoffroy was the person who was reported to have discovered it or isolated it. But basically, he was the one who was able to provide the distinction, and he demonstrated that it is distinct from lead and tin and other metals that everyone couldn't really tell the difference between at that time. Some of the practical applications. In medicine, bismuth subsalicylate is used as an antidiarrheal. It's also called pink bismuth, which we see it a lot in things like Pepto-Bismol, which gives it the pink color. It's the density difference between lead and bismuth, which is lead is 11.32 grams per centimeter cubed, and that bismuth is 9.78 grams per centimeter cubed. Allows it to be substituted for lead in a lot of several applications. For example, in ballistics for ammunition or anything related. For example, it can replace lead in birdshot, or it can also just be used in fishing sinkers or things like that. Bismuth is used in metal alloys with metals such as iron, and these alloys are very often used in automated sprinkler systems for fire alarms and such. And bismuth oxychloride is sometimes used in cosmetics as a pigment in eyeshadow and nail polish. It's also used in things like hairspray. This was used as a cosmetic in ancient Egypt and has been for a very long time. And it's got a little video to kind of wrap the whole thing up.
Group 15 is the Rhodes Gallery of the periodic table. Why, their name, pnictogens, even comes from the Greek word for suffocation. But suffocation would be the least of your concerns if you crossed paths with any of these deadly chemicals. Nitrogen is everywhere, making up 78% of the Earth's atmosphere. Okay, so maybe it's not deadly, but don't let your guard down just yet. Scuba divers all know nitrogen's most sinister attack. Nitrogen dissolved into the bloodstream can gather into bubbles while returning to the surface. These bubbles cause decompression sickness, also known as the bends, and it can be fatal. Phosphorus is a master of explosives. 4 of them bonded together form white phosphorus, which ignites when exposed to air and lays down a residue of phosphoric acid. Also, fluorophosphate esters are some of the most potent neurotoxins known. Arsenic is toxic to almost all life. Farmers use arsenic and its compounds for herbicides, fungicides, and pesticides. An arsenic compound, known as Agent Blue, was used during the Vietnam War to dry out rice fields and kill the crops. Antimony is poisonous to humans in a way similar to arsenic and can be fatal. Antimony leaches into liquids from polyethylene terephthalate, but I'm sure that this polyethylene terephthalate is an uncommon material you're unlikely to ever come into contact with. Oh dear! Bismuth is, oh my, bismuth is beautiful. No, don't be fooled by its beautiful rainbow crystals. This femme fatale can still be poisonous, primarily to the kidney, liver, and bladder. Still, bismuth is the least toxic of the pnictogens. Fortunately, ununhexium cannot be produced in large amounts, but its short half-life means that it would be very radioactive, but only briefly, attacking quickly before disappearing.
Way back with nitrogen, you mentioned that it's isolated from ammonium chloride and sodium azide. Where do they actually get the sodium azide from?
I don't know.
Most nitrogen actually comes from compression. So you can make small amounts of nitrogen using the azide. But most of the time we just put air under lots of pressure.
So with the bismuth, you said it gives pestobismal like its pink color. Like, does it have to be like combined with something else? Because it was like silvery in appearance.
Yeah, the compound bismuth sounds silent. I don't actually have the actual chemical compound, but that's what is referred to as pink bismuth.
Why is antimony useful? How about you look it up? That's it.
We have to finish that.
Oh no. Yeah, try getting it through the file open. Oh, you're. I think.
At Shell, we believe the
So I'm Wes Tatum, and this is my partner Bridget Lewis, and we're going to talk to you today about the Group 6A chalcogens.
So the elements of the chalcogens are oxygen, sulfur, selenium, tellurium, polonium, and likely livermorium, although they're not sure because they haven't been able to test all of its chemical properties yet. As you can see, they follow the typical trends. Ionization energy decreases down the table, as does electronegativity, and the radius increases. As you move down the table, all of the elements grow significantly less abundant, so oxygen being the most abundant. They all have 6 valence electrons, and usually have an oxidation number of -2. They form lots of acids like sulfuric acid, selenic acid, and all of the hydrogen chalcogenides are toxic except for water. Especially oxygen and sulfur, but all of them are relatively common in organic compounds, and they commonly bond to metals to form minerals. Oxygen, like I said, is the most abundant chalcogen, so it forms 46% of the Earth's crust. So you can see what a large section of the pie chart that is. It's the 3rd most abundant element in the entire universe. So its chemical properties are very different than the other chalcogens. This is largely because it's the only one that doesn't have an empty d orbital, and it is a non-metal. The oxidation states most common for oxygen are -2, but also -1 is fairly common. It forms the oxide, peroxide, and hydroxide ions, and it is highly electronegative. It forms compounds with almost all of the elements, and it commonly bonds with metals and metalloids to form oxides.
So there are 2 main isolation paths for oxygen. The first one is called fractional distillation, and to do that, they will cool down air into liquid form, and then they'll slowly heat it up so that what you don't want evaporates away. And if you do fractional distillation several times, you can end up with oxygen that is 99.5% pure. However, a quicker route to doing this is through passing dry air through a zeolite molecular sieve. And so that's just a crystal structure that has uniform and really, really small pores that only allows certain size molecules to pass through. Around 100 million tons of oxygen are isolated yearly, and of this, 55% is used in steel making, 25% is used by the chemical industry, and the remaining 20% is split between water treatment, because oxygen kills some forms of bacteria, steel cutting, liquid rocket fuel, and medical uses and other various things. Oxygen was isolated but not officially discovered until either 1771 or 1774. The main confusion was that Carl Wilhelm Scheele, he isolated oxygen by focusing a ray of sunlight on mercuric oxide, and he gathered the gas, which was oxygen, that was released. He did this in 1771, but he didn't publish his results until 1777, whereas Joseph Priestley, by the same method, isolated oxygen, but published right away in 1774. The main confusion about oxygen was that people thought of air as a single element as opposed to the conglomeration that we now know it is.
Sulfur is the next element. It is also the 2nd most abundant of the chalcogens, but significantly less than oxygen. It's the 17th most abundant element in the Earth's crust, and the 10th most abundant in the universe. Its common oxidation states are -2, 2, 4, and 6, and it forms sulfide, sulfite, sulfate, and thiosulfate ions, and the common mineral pyrite. Also, sulfide minerals plus oxygen form various gases. Organic compounds with sulfur have a very strong, distinct smell, which I'm sure you're all very familiar with.
Sulfur can be mined in its elemental form, but this process isn't as popular anymore, mainly because most of the gigantic elemental deposits have all been found, and the remaining ones are difficult to extract. There were large deposits found in Louisiana and Texas in 1865, and these were difficult to extract. So as a solution, in 1890, Hermann Frosch decided that he was going to pump superheated steam through the sulfur deposits, which melted them, and then allowed him to easily pump the sulfur up to the surface for extraction. However, currently, sulfur is more commonly isolated by refining it from oil, natural gas, and tar. Sulfur is commonly converted to sulfur dioxide and then on to sulfuric acid. Historically speaking, sulfur was a main ingredient in fireworks, and gunpowder, and concrete, and Greek fire, which is actually really cool. So Greek fire was the ancient Greek naval warfare technique. It was this closely guarded state secret. We don't know the recipe what it is today, but it had sulfur in it and probably a couple other compounds. And they would light it on fire, and they would throw it at their enemy ships, and it would burn even on top of water, without oxygen. It would just completely decimate any enemy forces. 60% of all of the sulfuric acid that is produced is used to make phosphoric acid. Also historically, sulfur was used commonly in alchemy, and it was isolated in the 1700s and 1800s and proved to be an element by those two French guys with complicated names.
So selenium is significantly less abundant than oxygen and sulfur. So it is the 67th most abundant element in the Earth's crust, and it commonly forms -2, 4, and 6 oxidation states. It forms selenides and selenates ionically, and there are some organic selenium compounds, but not a ton.
Around 1,500 metric tons of selenium are produced per year. 10% of this is gained through recycling. Japan is by far the largest producer, producing around 800 metric tons of selenium per year. Selenium is most commonly extracted from the waste. It's a byproduct of electrolyzing copper. And it can also be produced by farming selenium gathering plants such as milk vetch. And this method can produce up to 3 kilograms per acre. And even though this is a really cool, really efficient method, it's not really commonly practiced. Of the 1,500 metric tons, around 40% is used in glass making, 30% is used in metallurgy, and the rest is divvied up between agriculture, electronics, and pigments. It was initially discovered in 1817 by Jöns Jacob Berzelius. It was discovered when he found this reddish-brown waste at the bottom of a sulfur refinery, and he initially thought it to be arsenic or tellurium, but when he realized that it was a new element, he named it after the Greek word for moon.
So tellurium is one of the 9 least abundant elements in the Earth's crust. It's only found in about 5 parts per billion. It formerly caused -2, 4, and 6 oxidation states like lots of the other ones. It forms tellurites, and actually a rare mineral it forms is calverite, and it's the only element that can bond with gold. So in the 1800s, these 2 Irish guys were walking around, and they found an area where gold was everywhere. They could literally just go on a walk and pick it up off the ground. And they made the mistake of publishing the location, and so people came from all over the place. It was a crazy gold rush. It was called Cannon's Find. And a whole town built up. People started building buildings and roads out of the scrap rocks from the mining. But gradually, as always happens with gold rushes, the gold became increasingly difficult to find. People got a little bit desperate. But then one night, someone was lighting their campfire, and they started to notice that this yellow stuff was oozing out of the rocks. And it's actually because calverite decomposes really easily, and that's what was coming out of the rocks. So when the miners started to discover that this was gold, or they could get gold from it, the town went absolutely crazy, all these desperate miners for gold, and they started tearing down their houses and ripping up the roads and melting down all this rock to get the gold out. It's also for calverite and the tellurium inside that Telluride, Colorado got its name, because they had a similar gold rush. So.
Tellurium is mainly a byproduct of processing copper, but it can also be refined by the electrolytic reduction of sodium telluride. Between these 2 methods, between 150 and 200 metric tons of tellurium are produced per year. Tellurium suboxide is a mixture of tellurium and tellurium dioxide, and is the main constituent of the rewritable layers in CDs and DVDs. Bismuth telluride is used in microelectric devices, and cadmium telluride is one of the main constituents of solar panels. Tellurium was first discovered in 1783 by Joseph Euler von Reichenstein. He discovered it in a sample of calverite, which he thought was pure antimony, but he realized it wasn't. So he sent this unknown sample to a chemist named Martin Klaproth, and Klaproth isolated it and decided to name tellurium after the Greek word for earth.
Polonium is only found in very trace amounts on Earth. It's from the radioactive decay of uranium and thorium. It also is radioactive, and it's found less than 1 part per billion in the Earth's crust. It is one of the 10 rarest metals on Earth, forming the oxidation states 2 and 4.
Until nuclear reactors were common things, polonium had to be extracted strictly from uranium ore. But now it's mainly produced by bombarding bismuth and with neutrons. This only produces around 100 grams per year. Polonium is typically used in study as an alpha emitter, but it can also be alloyed with beryllium to be a neutron emitter, which is also used for study. Polonium was initially discovered by the Curies in the late 1800s. They found a sample of pitchblende that was emitting 4 times as much radiation than was accounted for by the uranium alone in the pitchblende. So they gathered up several tons of pitchblende and refined it slowly over several months, and eventually were just left with pure polonium, and they discovered it in 1898 officially.
So Marie Curie decided to name it polonium after the country of Poland and the Greek word from which that originates. She was born in what would be now part of Poland, but was at the time part of Russia. And as most of you probably know, historically Poland has kind of been a battleground for various countries. The boundaries get fought over a lot, it's been pulled apart several times. So Marie Curie was hoping that by naming the element polonium, it would create talk about it, kind of invigorate the movement to have Polish independence. But it absolutely did nothing. No one really cared, no one paid any attention. There was some gossip going on about her life that people cared about a lot more than polonium or Poland. So it didn't do anything, and it ended up being really ironic because polonium decomposes really quickly. It's relatively useless. At the time, she didn't know this, and it just ended up having a very negative effect on the Polish independent movement rather than helping it out like she had hoped. So, livermorium is the last element. It's always produced artificially from the bombardment of curium-248 with calcium-48. Only a very, very minute number of atoms can be created at a time. And as of 2011, only 25 atoms have ever been produced. So that's why at the beginning there, it had none of its physical or chemical properties. That's why I said they're not entirely sure that it is a chalcogen. They suspect it is, but can't say for sure if they haven't yet identified any of its properties. But it was first created successfully in 2000 by the Joint Institute for Nuclear Research.
And now we have 2 videos for you guys.
Yes.
World needs a broader mix of energies, which is why we are supplying that.
So this first video.
This is actually a reaction that involves 2 elements. We've got
We'll skip forward a little because she's talking. But
The first video is a reaction between elemental zinc and sulfur. They're just both in their solid forms and they're ground up. She puts them in the beaker and turns the beaker to mix them together and then dumps them into the cuboid.
We've got a mixture of our zinc and sulfur, and in order to start the reaction we're going to need a source of heat. And instead of using like a flame or anything like that, we're actually going to use a hot metal rod to get that reaction started. Neil's going to be in charge of the blowtorch, and I'm going to hold on to the rod. Okay.
we couldn't do this now.
see it has the green flame that's common to sulfur, and it's a really, really, really violent reaction. Slow motion.
And this actually just forms zinc sulfide, so it's a really simple reaction.
This is a similar reaction between iron and sulfur to create iron sulfide. To an expansion jar. Reaction, and it creates iron sulfide, better known as pyrite or Google.
Here's our references. Questions?
Do you know when they finally decided on the name for Livermorium? And what the abbreviation is?
The abbreviation is LB, and they probably decided on the name pretty close to 2000 when it was first successfully isolated officially. I didn't find it.
Don't know exactly.
Do you know why they use so much oxygen when they make steel?
Well, I mean, oxygen burns really well, so you can heat up stuff with it. Steel cutting, it also helps with the making of alloys.
They stick the oxygen into the actual furnace that has the liquid stuff because it pulls all the impurities out of the steel. That's like that on steel.
Give you a minute to finish your feedback and write a question. Write one to the other side of your back.
Put it right here on a nice little pile. Oh my God.
Okay, so like promised, we're going to talk about P-type semiconductors. This is not. So if it's going to be the opposite of N-type, what was N-type? Extra electron. This would be short an electron. very small amount of gallium in a silicon structure. Our network of silicon, and then we put in something that is missing an electron, right? So that spot where an electron should be is a hole. And it's P because it's a positive charge, or one short of an electron. But what they really talk about is making holes, making spaces where there's a shortage of an electron. And if you have a hole, it talks about the hole moving. But the hole doesn't actually move, right? It's the electrons move towards the hole, right? Because if you've got a positive charge, the electron is going to move towards it. And that'll look like the hole is moving along the structure, when it's really the electrons are moving towards the hole. We can put in aluminum into silicon, but they don't like each other. They kind of separate. So that's why we went down the grade too. Okay, so redraw our silicon MO diagram, band diagram. What does it look like? We should be good at this one. We've done it 2 times. This will be the 3rd.
It's got 2 bars.
Energy goes on there. It's got 2 bars. It's got a band gap of 1.1 electron volts. This one is filled. Because each silicon is bringing 4 electrons out of the 8 total electrons for each atom, so it's half full. And so if you remove an electron, sometimes they write it with a little space right there and kind of make it look like we've removed electrons from that band. But a more common and probably more accurate description is to put a conductance band, right? And I'm making it smaller because more like a combination of density of states and MO diagram. There's not very much of the dopant in there, so that's why I'm making it smaller. And that's the antibonding layer. And it's closer in energy to the bonding. And so what can happen is the electrons can come up to the conductance band of the dopant. And once you get electrons moving, then you can have the semiconductor properties. So basically you're filling in this little one. How's that different than the N-type? Yeah, so the N-type, it's a filled band, and the conductance happens by promoting to the antibonding of the silicon framework. Here, the electrons are promoted to the antibond of the hole. So these are only really cool if you put them together. Pretty much all of electronics are based on p-n junctions. And so we're going to make a picture that doesn't quite match what we just did. So it's because it leaves out one detail. Okay. So we have our full valence band. Okay, and then we have our conduction band. And they didn't draw in the little teeny gap or the little teeny amount of our holes. They just said, okay, well, some electrons are going to get into a conduction band. They're not specifying that it's from your dopant in this picture. And this picture is taken from your book, so I wanted you to be able to understand both. And then, if we put it with an N-type, N-type tends to have lower energy valence bands and the conductance band, so we're going to have this whole connection here. Can you tell a difference between the P and N-type with this picture?
No.
No, it's just the energies are different, and usually the N-type is lower energy. It's easier to pack an extra electron in than to remove an electron. So it's really once those electrons get propagated. So once you take these electrons out of the N-type, and you start populating up here, and you take the valence band over here and you have a little level or a little hole. So that's why it's not looking like this, because we're going to move some there, put some extra electrons in. What that will make is if we put a current in, it matters which way we put this current in. If our current goes that direction, what is current?
Moving of
Movement
electrons.
of electrons. So where are electrons coming from? They're coming from right here, the conductance band of the N-type. And what's similar energy? The P-type gap. And so the electrons are going to flow, and we'll get, as they draw pictures, the positive holes moving that way. Okay, cross over here. So you get some positive holes building up over here. Are the positive holes moving? No, the electrons are moving towards the positive holes, filling them, and then that leaves a gap where the electrons left. We have to, of course, make sure that we've lined this up so our positive and negative kind of electrodes, where we're going to apply the voltage so we can get a current. And we have to line up the positive with the p-type because we need the electrons to flow towards the positive voltage, and we need the electrons, the holes, to move towards the negative. At some point in time, you're going to reach a point where this doesn't work, right? You've moved all of the electrons to the p-type. You've moved all of the holes over to the n-type. And so when we reach equilibrium, we stop. The current doesn't flow anymore. And so we would call that in electronics a forward bias. So we forwardly bias the p-n junction. So that the electrons flow only one direction. They can only go from the n-type to the p-type. And that will be the basis of diodes. It'll be the basis of LEDs. So we will do those.